Hi there, this is Prof. Johan from the Department of Chemical Engineering at the University of Pretoria. Welcome to my series on the Introduction to Chemical Engineering and Chemical Engineering Principles. In this video lecture, I want to continue on hydrostatic pressure and specifically talk to you about shape and volume and the effect that this has on the hydrostatic pressure of a system. So let's look at two tanks. I have on the left hand side tank number 1, and on the right hand side I have tank number 2. Tank number 1 filled with water, tank number 2 filled with water, and the important thing about these two tanks is that their height is exactly the same. So the area at the bottom of this tank is A1 and the area at the bottom of this tank is A2, and it's clear that A1 is much smaller than A2. Now we know that pressure equals the force divided by the area. So let's calculate P1 and P2 at the bottom of the tanks. So let's start with the one on the left and say P1 equals F over A. F equals the mass in 1 multiplied by the gravitational constant over the area at the bottom. We can say that the mass equals to the density multiplied by the volume in 1, gravitational constant over A1. We can now say that the volume equals the area at the bottom multiplied by the height of the tank multiplied by gravitational constant, and suddenly these two areas cancel out and we have that P1 equals rho G H1. We can do exactly the same on the right hand side, and I am not going to bore you with the calculations. And there we have it. But we know that H1 equals H2 equals H, so we can get rid of those. And this implies that these two pressures, P2 and P1, is exactly the same. It doesn't matter what the volumes in these two tanks are, as long as the height of the hydrostatic force is the same, the pressure at the bottom of that hydrostatic volume will be the same. Let's now take this to a whole new level. Here we have several new shapes. Let's call this one number 1, this one number 2, this one number 3, this one number 4, this one number 5, this one number 6. And for all of them, I want to know what is the pressure here at the bottom, and let's call this total height again H. So what is this pressure at the bottom? And like we did with the previous set of calculations, I do not care what the shape of these tanks are at the top, nor what the shape of these tanks are at the bottom, nor what path they follow. As long as the total height is the same, we know that pressure at the bottom for 1 will be equals to the same as the pressure at the bottom of 2, the same as the pressure at the bottom of 3, the same as the pressure at the bottom of 4, the same as the pressure at the bottom of 5, the same as the pressure at the bottom of 6, which would be equals to rho G H. It is important to note that if all the tanks are the same height and, very importantly, contain the same fluid, which means have the same density, that the pressure at the bottom of these tanks will be equal, irrespective of the path the fluid has to follow, the shape at the bottom or the top, or the volume contained in these tanks. Thank you for watching.